Hello everyone! Today we're going to be discussing the basics of hybrid bonding for advanced 3D packaging. My name is William, and I'm really excited to introduce this technology to you guys because it's an innovative technology that's really going to enable the next generation of packaged devices. So we'll start with the history of interconnect technology and review some of the existing techniques that are currently used to enable the devices we interact with on a daily basis. From there, I'll describe the concept of hybrid bonding and how the technology came to be. Then, I'll address the main benefits of hybrid bonding and the advantages it has compared to the existing methods. Finally, I'll explain the fabrication process to provide you with a fundamental understanding of what's going on and some of the methods that are used to evaluate the quality of the bond once the fabrication process is complete. And with that being said, let's get into the content. The first type of interconnect to be implemented with integrated circuits and packaged devices in general is the wire bond. And the wire bond is simply a wire that's typically made out of a conductive metal, like aluminum or gold, that forms an electrical interconnection here between the die and the substrate. And these metal wires are secured to these bond pads using metallurgical welds, and they're relatively simple, reliable, and pretty easy to manufacture in a high volume. Solder bumps are a slightly more advanced form of interconnect, but they're still relatively simple. They effectively replace wire bonds and allow for a shorter, more direct connection between the die and the substrate. And more importantly, they enable this flip chip style of connection, which is widely used in both simple and advanced package devices. They improve upon the wire bonds in almost every aspect, being less expensive and providing better performance and reliability. Now, perhaps the most advanced form of interconnect, other than hybrid bonding, is the silicon interposer, which is this layer between the substrate and the die that uses a redistribution layer to redirect connections horizontally and through silicon vias to form these connections vertically. And combined with these solder bumps, the silicon interposer enables heterogeneous integration, which is essentially just multiple dies in a single package. And the silicon interposer transforms the simple connection style of solder bumps into a much more complex system that has a huge capacity for intricate designs that allows connections to be precisely routed from each die to various IOs on the package. So now we finally get to answer the big question, which is what exactly is hybrid bonding? And simply put, it's this dielectric bond alongside this metal bond that forms an interconnection between the two wafers or dies that effectively replaces these solder bumps with an even more direct connection. And this processing is done at low temperatures to initiate high bond strengths. And having the ability to process the components at low temperatures is really beneficial because it means you can stay within your thermal budget even after the back end of line processing. And if you're not familiar with the concept of a thermal budget, essentially it refers to the maximum temperature you can process the wafer at while avoiding indirectly damaging existing features that have already been designed onto the wafer previously. And by processing at a lower temperature, you can assure that no features will be inadvertently altered by the increase in temperature. The first form of hybrid bonding actually had nothing to do with a hybrid bond, but was instead a technique called homogeneous direct bonding, and it was first invented by the Research Triangle Institute and patented as Zybond. Now, homogeneous direct bonding was a process where a very thin dielectric was formed on the surface of a wafer, polished smooth, and then activated via plasma to become hydrophilic, so that when the two wafers were brought together at room temperature, they would form a spontaneous bond through a process called hydrophilic oxide-to-oxide bonding. Now, a spin-off company of RTI called Ziptronics developed the technology into the direct bond interconnect, which is commonly known as the hybrid bond. Now, what Ziptronics did is they incorporated these small metal pads within the dielectric layer that could be aligned and bonded through an annealing step after the spontaneous bond had been formed between the oxides. Ultimately, this would form conductive connection paths between the two wafers. The need for this technology really comes from the rapid innovation and miniaturization of devices that demand a greater density of interconnections in order to either maintain or increase their functionality while still making them smaller. And the main way to increase this interconnect density is to decrease the interconnect area. And the only way to do that is to decrease the pitch size of the interconnections themselves. Now, current interconnect technologies are limited by electrical and thermomechanical restrictions. So normal solder bumps are limited to a pitch size of about 100 micrometers. And even these micro bumps shown here are limited to a pitch size of about 20 to 50 micrometers. Now, the main benefit of hybrid bonding is that it allows for the pitch size to be decreased to about 10 micrometers and sometimes even smaller, which allows the interconnect density to be increased by nearly 2 orders of magnitude, which is amazing. While this is a huge improvement, it also requires insane precision. And a cross-section is shown here to help you visualize how these interconnects align with another between dies and why this precision is so important when the bonding process occurs. A huge benefit of hybrid bonding is also the improved electrical properties that you get with the technique. Now, because the connections are so short and direct, it reduces the overhead, or the latency, as well as the consumed power to operate, and allows the interconnects to function like a single monolithic package. And the generated capacitance between the interconnects is also reduced by nearly 90% compared to solder, and the direct connections help reduce eddy currents that could be generated by inductors that are placed near the interface. Alright, now we can begin to talk about the fabrication process itself. The most important preparation step is making sure that the dielectric surface is as flat and clean as possible. The nanoscale topography is extremely important because any small particle or defect that's present on the surface prior to bonding could result in tens to thousands of failed connections. A single particle or defect could cause this large void area to form between the wafers, which would disrupt the bonding process between the metal pads, ultimately ruining the whole process because none of the connections would function properly. And the smoothness or the low dielectric roughness can be achieved through a process called chemical mechanical polishing, which is typically a proprietary process that's unique for each manufacturer because they all have their own slurry recipes and polishing parameters that they use. And the second preparation step to keep in mind is the recession of these metal pads from the dielectric layer to form this dishing gap, which is something that will be important during the annealing process. Now, this dishing gap must be consistent across the wafer for every single metal pad in order to ensure a consistent and strong bond for every single interconnection. And the planarity of the wafer can be measured using an atomic force microscope in order to evaluate the magnitude of the dishing gap. And an example AFM measurement can be shown here across one of the metal pads, where the difference in height is extremely small. It's around 20 nanometers from the top of the dielectric layer to the top of the metal pad. The bonding process, as mentioned previously, involves these two wafers being bonded together. And the first step in this process is activating the dielectric surfaces of each wafer with plasma to be hydrophilic, just like they are in homogeneous direct bonding. And this surface activation can be evaluated using a contact angle measurement. And once the surfaces are activated here in step A, they're brought together at room temperature and undergo a spontaneous bonding process called hydrophilic oxide-to-oxide bonding here in step B. Now this process forms a very strong bond between the dielectric layers of each wafer, but it leaves this dishing gap between the metal pads of each wafer, which is not illustrated to scale here at all. In order to fill in this dishing gap, the system has to be annealed, usually to a temperature of around 300 degrees Celsius. Now, because the coefficient of thermal expansion of the metal is typically much greater than the coefficient of thermal expansion of the oxide, the dimensions of the oxide will remain relatively constant compared to the dimensions of the metal. And here in step C, the metal will expand due to the heat and it will close the dishing gap, bonding the metal pads of each respective wafer to one another. Here in step D, as the metal continues to expand after filling the dishing gap, the internal pressure and the sustained heat will effectively increase the driving forces for diffusion and allow the crystal structure of each metal to form a strong bond with one another, and it will also allow the crystal structure to relax, reducing the defects and grain boundaries that could scatter any conductive electrons that are trying to move through it. Effectively, the interface between the metal pads is annihilated, and the two metal components come together to form a single crystal. Once the fabrication process has been completed, the quality of the bonds has to be evaluated. Ideally, there should be no voids, grain boundaries, or other defects that could potentially reduce the conductive efficiency of the metal interconnect. And one way this can be done is using a scanning electron microscope, which can be used to search for any defects along the bond interface. An example of an SEM image can be seen here, where you can see the bond interface and visually identify any defects, as well as check for the alignment of the connections. An SEM can also be combined with an EDS to generate a compositional map of the bond interface, which could help identify any impurity elements. Now, the bond quality can also be evaluated with a technique called scanning acoustic microscopy, and one example of an SAM measurement can be seen here, where the quantity and the size of voids present in the bonded area can be easily detected. Another version of an SAM measurement can be seen here in cases 1, 2, and 3, where the ideal case is this case number 3, where there's virtually no indication of an interface between the two metal connections whatsoever. One final consideration is the placement accuracy of the two components when they're brought together during the hybrid bonding process. Due to the extremely small pitch sizes that are supported by hybrid bonding, the placement accuracy is exceptionally crucial when forming these bonds. Taking a look at this cross-sectional image, if the wafers are misaligned by as little as a few micrometers, it can cause connections to be misaligned, improperly connected, doubly connected, or bonded to completely different connection sites than initially intended. And this would cause the whole bonding process to be a failure, making the wafer useless. So to mitigate this, factors such as the size, shape, and contrast of this calibration symbol can be optimized to improve the computer's ability to orientate itself in space and respective to the wafer. Other factors such as the polishing, dicing, and surface protection of the wafer can be optimized to improve the die's quality as a whole. But some other factors, such as the vibration, the cleanliness, and thermal controls of the tool, can be optimized to improve the tool's ability to properly align the wafers. Also, correcting the bond head parallelism, or how parallel the wafers are to one another when they're brought together for bonding, can also help to improve the quality and consistency of the bonding process. Alright, and that's all I have about hybrid bonding to share with you today, so I'd like to thank you for joining me, and I'll see you in the next video. Take care.